In this section, we're going to explore our log as a function and look at properties of the function such as domain and range and so on. So just recall our exponential function. F of x is equal to a of x, and imagine we replace the f of x with y, and then we exchange our x and our y. And what we get is our log, which is y equal to log base a of x. And that tells us that the inverse function of our exponential function is our log function, which I had mentioned earlier in the prior section, but now we're going to explore this idea a little bit further. And then this brings us to our log function, which says for a base that is not only positive but not equal to 1, again, positive makes it a function, not equal to 1 makes it a one-to-one function. And here I have a little typo there. There's that weird I. It shouldn't be there. It should just be the x greater than 0. Now remember, x is the argument. So if these conditions are met, here, let me be really clear that that I shouldn't be there. So if those conditions are met, then our f of x, our function, which is just our y value, is equal to log base a of x. Again, x is the argument and it needs to be greater than 0. So this is a logarithmic function with base a. What we're going to do next in example 1 is we're going to graph the exponential function f of x equal to 2 to the x, which we had done in a prior section, and then its inverse, g of x, equal to log base 2 of x. So same base, one's the exponential, one's the log function. They should be inverses of each other. And we're going to verify that. So remember, if they are inverses of each other, then they should reflect, oh, this is a sad dashed line, across y equal to x. So it should reflect across this line. Let's go ahead and graph f of x. So I'm going to replace the f of x with y equal to 2 to the x. Graph that exponential function. And I'm going to do what I did in the previous section. I'm just going to put in 2, 1, 0, negative 1, negative 2 for my x values. So 2 squared is 4, 2 to the 1 is 2, 2 to the 0 is 1. Then I have 1 half and 1 fourth. We'll graph 2, 4. 1, 2, 0, 1, negative 1 half, negative 2 is 1 fourth. And this would be our function f. Something to notice is f has a horizontal asymptote of y equal to 0. So you could see that it approaches the y equal to 0. And I'm going to use green for the log function g. I am going to rewrite this as y equal to log base 2 of x. And that's still too difficult for me to figure out how to get points with. So I'm going to translate that back to its exponential form. That would give me 2 to the y equal to x. When I make my table of values, it's going to be really hard for me to figure out the y value. So I don't want to put in x values and try to figure out what y is. It would be better if we put in the y values. So I'm going to put in 2, 1, 0, negative 1, negative 2 in for y, and then see what the x is. So if I put 2 in for y, I get 4 for x. 1 would give me 2, 0 gives me 1. Negative 1 would give me half. And then I have 1/4. So far, it's doing exactly what I think it should do. Notice that y equal to 2 to the x, the blue graph, if I exchange the x and y values, I get my green graph, which is my log function. Let's go ahead and graph those points. We have 4, 2, 2, 1, 1, 0, half, negative 1, and then we have 1/4 would be negative 2. And it looks like it reflects across that axis of symmetry y equal to x. So something to note is that my function g has a vertical asymptote of x equal to 0. And that makes sense because we switched our x's and our y's, we also switched our asymptotes. So where we had a horizontal asymptote of y equal to 0, that becomes a vertical asymptote of x equal to 0. The other part of this question was to state the domain and range for each function. When we look at our function f, and I'll just write DOM for domain, the domain of f is, it looks like I could put anything in for x. I would say all real numbers. And then when I look at the range, that's where I'm going to have an issue. I don't get any y values that are less than 0. So it looks like my y values, my range goes from 0 to infinity. And it's a parenthesis around the 0 because we don't include that. Looking at g, the log function, I see the domain of g is x values, right? So my x values here have to be greater than 0. And then the range would be the y values. It looks like I get all the y values from negative infinity to positive infinity. Yeah, I'm just looking at the graph here. And this makes sense as well. We exchange the x and y's, which means we're also exchanging the domain and the range. So it's clear that these two functions are inverses of each other. So now that we know that the log function is a function, we need to talk about the domain. The domain has to be, the argument has to be positive. It cannot be negative or 0. So it's very simple. If you have a log function, to find the domain, all you have to do is set the argument. So in example 2a, the argument is 2x minus 9. All I have to do is set that strictly greater than 0. So the argument can never be negative, can never be 0, always has to be positive. And then solving this, I would add 9 to both sides and then divide by 2. So my domain here for my function f is going to go from 9 over 2 to positive infinity. Let's do this again in b. We have our function f log base 7. And notice it doesn't really matter what the base is. We're just looking at the argument. In this case, it's x squared minus 9. So that x squared minus 9 has to be greater than 0. Here, because it's an inequality and it's quadratic, our strategy is to factor. This would be difference of squares, x plus 3x minus 3. And then look at some test points. So remember, we're setting this equal to 0 to get x equal to negative 3, x equal to positive 3. Those values are what we're going to do to break up our number line. And since it's strictly greater than 0, we don't use these endpoints. So the domain will either go from negative infinity to negative 3 with a parenthesis, or parenthesis negative 3 to positive 3, or parenthesis 3 to positive infinity. If I were to pick test points, maybe I would do a -4, 0, +4. And when I put -4 into the inequality, I get 16 minus 9, which should be positive. So what is 16? Yeah, 16 minus 9, is that greater than 0? Yes. So I can use anything from -infinity to -3. If I put in 0, I get -9 greater than 0, which is false, cannot use. If I put in 4, again, I get 16 minus 9, that is greater than 0. In this case, the domain of the function is going to be -infinity to -3 union 3 to infinity. And let's do one more just as a reminder of inequalities with rational expressions. So in example C, I have x plus 1 over 5 minus x, that has to be greater than 0. So the idea is to figure out x values that give you 0 in the numerator and denominator. In this case, we have -1 and x equal to +5. As we did with the quadratic, we would go ahead, maybe I'll put the number line here. We would go ahead and break up our number line. We have -5 or -1 and 5. Strictly greater than 0 means we're not going to use either one of these points when we figure out our interval. So possible domain would go -infinity to -1, all with parentheses, -1 to 5, 5 to infinity. Let's see, test points, maybe -2, 0, and 6. Those look good to me. If I put in -2 into the inequality, I get a -1 over a +7. And is that greater than 0? No. If I put 0 in, I get 1 over 5. Is that greater than 0? Yes. And then if I put in 6, I end up with 7 over -1. Is that greater than 0? Nope. So my domain for this particular function would be the interval from -1 to 5. Okay. So we're going to just briefly look at some graphs of transformations and just simple transformations. The transformations are going to do exactly what we expect it to do. In example 3, we want to graph f of x equal to log base 2 of x plus 3. So notice that +3 is not part of the argument of the log because the x plus 3 is not in parentheses. So really what this is saying is we're going to do log base 2 of x. That's going to be our basic or our parent function. And that +3 is going to be, as we expect it to be, a shift up 3 units. So the first thing I want to do is graph that parent function, and that would be y equal to log base 2 of x, which we graphed before. Remember, the strategy here is to switch it to its exponential form, which would be 2 to the y equal to x. And then get some points by putting in values for the y. And the usual one would be 2, 1, 0, -1, -2. That's more than enough points, which would give us 4, 2, 1, half, 1/4. So 4, 2, 2, 1, 1, 0, half, -1, and so on. This is not the final graph. So remember, this is the basic or the parent function. And then that plus 3, we're going to go ahead and shift up 3 units. So again, this is doing exactly what we thought it would do. Maybe I will use black. So I'm going to shift up this, what's 1, 2, 3, and then at the half, I got 1, 1, 2, 3. At the 0, I go 1, 2, 3, 2, 1, 2, 3. At 4, 1, 2, 3. And this becomes my function. So again, the transformations are what you would think they should be. Let's try another one. Oh wait, something I did want to note is when I shifted up, I didn't change my domain. Remember, the domain is the x values. The x values did not change, and that's because that vertical asymptote did not change. Maybe I'll just kind of sketch the vertical asymptote in here to remind you that we have a vertical asymptote at x equal to 0. So since the vertical asymptote, which is x values, since that didn't change, neither did my domain. And my range was all real numbers. It's still negative to positive infinity. And then we'll just do one last example, and then we're done with this section. So notice that I'm adding 3 to the argument. I'm changing my x values. As before, whenever we change the x values, it's going to do opposite of what we think it should do. So this should be a shift left by 3 units. Let's go ahead and look at our y equal to log base 2 of x. Again, that was our basic or parent function. It's going to pass through 1, 0, 2, 1, 4, 2. It's going to go this way, and then half, and then it gets closer and closer to that y-axis. So now I'm going to shift left 3 units. I'm going to take these points and go 1, 2, 3, 1, 2, 3, 1, 2, 3, shift them all, 3. Notice, because I am shifting along the x-axis, I am changing my vertical asymptote. It is now x equal to -3. So that's my new vertical asymptote. So what that did is it changed the domain. The domain now for my function is going to be equal to -3 to positive infinity. Let me label this as my function f. So I think that's it for this section. Really short section. We're just looking at properties of functions with log. So that's it.